Hi. So we are working towards a comparison of recommender systems and LLMs, and we're going to propose a point of view on how to get there. But one key part of it that we'll deep dive on in this video is that the retrieval part of recommender systems is actually very similar to pre-training today. So my focus will be on pre-training and retrieval, but I'll just give you the context before I get there. Um, so an LLM pipeline is has three broad steps, three broad parts. So one is pre-training, supervised fine-tuning, and then reward maximization. Pre-training is about um, optimizing the parameters of the model using next token prediction loss. And this is exactly what we'll say is the retrieval setup in recommender systems. So to be specific, pre-training is described as training an LLM on a lot of data, not necessarily limited to the exact domain you are going to apply the LLM on. Imagine you are applying an LLM for, I don't know, a chatbot for customer service or something. But pre-training does not restrict you to training only on such data. So that's kind of the difference between kind of supervised fine-tuning being curated high quality in domain data, but pre-training massive token logs. But that technicality aside, the main loss that you are optimizing for in both these steps is next token prediction. I mean, given a certain context, you're optimizing the model to be more correct in or improve in accuracy in predicting what is the next token after this. So this video is really about pre-training or SFT in LLMs is very similar to recommender systems retrieval. And to explain why we are mentioning this point is that once you break out the parts of LLMs and see which parts are already similar to recommender systems, then you can hone in on where there might be opportunity. So the reason we are going into this topic today is to understand that this part, like generative retrieval, or is an evolution, but not a revolution from recommender systems retrieval, because retrieval today is already the same as what pre-training and slash SFT is in LLMs. So it's a somewhat contentious point of view. So I'll go over it step by step. So pre-training LLMs is next token prediction over about 100,000 vocabulary tokens. That's the current state of the world. Both systems, by both systems I mean pre-training and embedding-based retrieval in recommender systems, both systems embed the context into a vector. They compute dot product based similarity between this vector and a large embedding matrix. And people who have not seen pre-training this way, I'll explain how mathematically what pre-training does, which is estimate the probability of the tokens, can be looked at as computing dot products. Keep that in mind for a second. And then both systems produces a distribution over the discrete items or tokens with softmax or sample softmax loss. And both systems then train using cross entropy with this probability. So one of the things I claimed is that pre-training is similar to an embedding-based dot product. The reason I'm claiming this is if you in a pre-training setup, what you're doing is you are computing the probability of each of the valid tokens, and then checking, or rather the loss is how close to 1 was the probability of the true token. And that is what is described as next token prediction loss, right? So among all your tokens, you estimated the probability of them being in the next one at a certain point in the context. And then you have the ground truth data, whatever was the next token. So you try to maximize this. You try to change your model such that the estimated probability of the ground truth token is highest. That means you have sort of a neural network, which at some point is outputting the prediction of each of the tokens. If you look at the last layer of this neural network, I'm calling that edge here, then the output for a single token, the ith token, is nothing but edge transpose wi, where wi is the neural network weight matrix between the last layer and the between all the tokens. Because the last layer, let's say the dimension of h is d. Okay, so you have a neural network which at the last layer has d inputs, and it needs to have v outputs. V is the size of the vocabulary. So the W matrix is of dimension D input times V output, right? Because it needs to multiply the input and produce the output. So a single WD, like the ith row of this, basically W colon I, you can think of it as the embedding of the ith token. And hence, this is exactly the same as taking a dot product between the embedding of the context and the ith token. So what I'm saying is actually very similar to what Mikolov et al.'s word to vec paper was. Let me see if I can find it. So if you look at the word to vec paper, this was 2013, it says the same thing, that and given a context, the probability of a word is the dot product in the softmax. It's called the softmax. The softmax of the dot product of the context and the the context and the word being output at this point. So W, like O is for output and I is for input. Probability of output given input is softmax of these embeddings. Okay, and this is exactly what we do in retrieval as well. In two-tower models, we also consider there's a user embedding and an item embedding, and we say that and we train it with softmax loss, which means that the estimated probability of the true item is again the same, like e to the don't have the formula here, but e to the power dot product of user item embeddings divided by sum over all items in the batch, e to the power user item embedding. So the loss of next token prediction and next item prediction is exactly the same. The only difference was that due to the vocabulary being small enough that you can do a full softmax in pre-training SFT, you're actually doing a full softmax, right? So this sum that we have here, sum over the vocabulary, this is feasible in LLMs. But in like most recommender systems, this is large enough that you have to sample the negatives. That's practically the difference. If it was not the case, then literally the loss would be the same between recommender systems and retrieval. There are differences, of course. In LLMs, the data is of lower quality. I think all the data that you train on in recommender systems are actual user interactions, right? So there's no spam, there's no, yeah, in general, there are differences between these domains. But mathematically, these two are very similar. So loss is how different these probabilities are from the ground truth observation. LLMs can compute this loss in the number of valid tokens of 100,000. The industry recommends 100 million. Mikolov et al., the same word-to-vec paper that I was showing, the word-to-vec paper that I was showing, they describe two ways to handle this very large corpus. They say you can either do hierarchical softmax, that means you sort of have a tree, and you say that my probability of getting to the right place is I need to sort of be right about every step. For the people who have been following generative retrieval, this will ring a bell. This is actually the direction that they're going as well with hierarchical clustering. And then you have sample softmax, which is what most of our recommended system retrieval uses today. They use largely in-batch negative sampling. It's very efficient, and it's, the training GPUs and are very optimized, etc. More recently, with papers like Tiger from YouTube, they have shown that you can actually use hierarchical clustering based approaches to use full softmax in retrieval. So that's one direction. Another paper that I want you to learn about is this recent one by Subaya et al., an efficient item ID generation. This is also a Google research paper. What they claim is that you do not need to use semantic IDs. You can actually use item IDs for generative retrieval. At a very high level, what they're saying is, I don't know if they have a nice image here. So you have your full softmax. Then what they claim is, let's do a 2-level softmax. Let's add the cluster. Yeah, I think this is a good description of what they're saying. But let's cluster our items, recommendable items, and then let's learn to be good at predicting the cluster. And then among the items in the cluster, let's be good at predicting the item. And it feels similar to hierarchical software, but when you have a special two-level case, you can actually implement it very efficiently in a GPU. Okay, so this is, I think, the key summary. The probability of a certain candidate given the context, or in this case, probability of a token given the context, is probability of the cluster of the token multiplied by probability of the token given the cluster and the context. Why I'm saying this is because once you start thinking of retrieval in this way, then this is a very minor addition to the current 2-tower setup. So, So all we are saying is, in the current embedding-based approaches for retrieval, let's add a cluster loss and let's use that for inference. And we are almost at generative retrieval. So my conclusion is that if towards the journey of making recommender systems learn from the advances of LLMs, in retrieval, we are already very close. And directions similar to this cluster-based approach from Google, they are inspiring. They're also evolutions, not revolutions. They are also things you can do with minor changes and quickly see if they're helping your domain or not. you don't have to like drop everything and do something completely new from scratch to get the best of LLMs in your recommender system. Yeah, thank you.